Yeah, hi, welcome everybody to the University of Washington Robotics Colloquium. It's my great pleasure to introduce today's speaker, Michael Beetz. Michael and I, we've been friends for more than 20 years, I think. We actually shared an office, right? We shared an office at the University of Bonn, where I was still working on my PhD, and Michael just came back fresh from finishing his PhD at Yale, right, and then did a postdoc position in Bonn. After that, he moved on to TU Munich and is now a professor at the University of Bremen. Michael's work in robotics has always taken, I would say, kind of an AI approach to this, right, where it's more about the high-level reasoning. How can we get robots to plan about things in the world? How can we get them to still do this reactively and not just kind of in an open loop fashion, but always take sensor feedback also into account when they make their decision. He's done some really cool work on leveraging information that we might have from knowledge bases, from the web. He also did this no-ROB, right? One of his projects was like, how can we build kind of an internet-based or internet-scale knowledge base that all the robots can share and that they can learn from each other's experience. And today he's going to talk to us about exactly related to this knowledge reasoning and also, I guess, how all of this might leverage physics-based models about the world. Welcome, Michael.
Thanks a lot for having me here. Thanks a lot for the introduction. Yes, so I want to talk a little bit about the more traditional way of applying AI method to autonomous robot control. And I'm very interested in robots that accomplish human-scale manipulation tasks. So I would like to have robots doing goal-directed manipulation tasks, such as setting table, cleaning the table. And the question is, how can we write computer programs that can achieve that? And this is a topic that we investigate in a collaborative research center in Bremen. And I can just give you a little bit of an intuition of what it is that we are after. We are essentially trying to push manipulation capabilities from kind of just doing that to mastering.
After many years of research, we're now at a stage where our robots can perform complex manipulation tasks, but only in specific contexts, for specific objects, and under specific conditions. The transition should be to mastering human-scale manipulation tasks in realistic and open situations. If we want to go from current robots to mastering activity robotics, the key point is knowledge. The robot will only get key point task descriptions, such as drop something from the pot, and it will need to know that it means tilting the pot, that if it tilts it too much, it will spill, not too high, not too low, and that the weight in the pot will change. The question is, how to get the common sense and naive physics into robot control systems and make it effective so that it basically does its job without delaying the performance. The robot should not have to wait a long time until the reasoning problems are solved. The reasoning should be ubiquitous, so fast that you don't notice that it's there.
So that's the kind of manipulation capability I'm dreaming of. And the question is, how do we get robots of actually doing that? There's another way of looking at that, right? When we look at how we as humans acquire such manipulation skills, And it's pretty amazing that even a boy that is not even 2 years old is able to do things like getting something to drink, right? And it basically takes the water out of the pot, fills it in the glass. He is composing different motions like grasping, translating the pot, and then tilting it. He's also aware of the objectives and also the negative side effects. He is careful in avoiding spilling, right? And he even uses the cup in order to stabilize the pot and to perform the action kind of more robustly. And that's pretty amazing, right? Because at that time, the boy certainly has not the language concepts in order to talk about all these things, but still, even at that age, they already have the common sense and intuitive physics understanding to do these tasks. And then if we look at human and how they evolve their manipulation capabilities over lifetime, right? So step by step, we acquire different methods for pouring, and even like pouring like a barkeeper, throwing up a bottle, catching it, and filling a glass. And we can do that by observing others doing these manipulation actions, by reading, playing, or exploring. And so one of the assumptions that is underlying the work in our lab is that we can build robot control programs that have the elementary proficiency of the capabilities of the 2-year-old. But we can design these robot control programs very carefully, that they are very modular, very transparent, so that, that computer programs can automatically reason about that, and that they can involve all these other methods of doing these tasks by transforming this basic and general robot control program. So in this talk, I want to invite you to look at a little bit at getting these manipulation skills from a programmer's point of view. And I want to convince you that for one thing, that it's possible that we can think of these very general plans that can handle action verbs such as fetch, place, cutting, pouring, and that we can combine these very general plans together with knowledge, and then we come to a skill level which lets us handle these manipulation tasks even under open conditions. I then will propose a hybrid reasoning system that tightly couples simulation-based reasoning with symbolic reasoning, and then finally I try to demonstrate what we gain if we are kind of combining these different reasoning capabilities, and what we can learn and what kinds of decision making we can get in our robots. Okay, so the key problem, if you think about humans doing manipulation tasks, being manipulation tasks that we are getting from others by language instructions, or if they are self-made tasks, is that we get tasks like perform an action type pouring, where the theme is some substance of type water. So we get very underdetermined tasks, which only kind of spell out explicitly some aspects of the task, but many others are left out. And if we are getting such an underdetermined task description, we have to infer things like grasp the pot by the handle, hold the pot horizontally, tilt the pot around the axis between the handles, hold the lid while pouring. If a robot cannot infer these kinds of missing pieces of information, then there is no way that we can actually apply manipulation actions to situations that we haven't directly experienced before. So kind of that is one of the key functionalities that a knowledge-enabled robot control system must have. So the challenge that I'm trying to focus on in my research work is the question if you see that robot in the popcorn making tasks, is there, if you are just looking at the fetch and place tasks, can we have a single program that can generate all the fetch and place behaviors that we have seen here? Then can we go on and basically replace objects that were used in that scenarios by other objects, and the program still works? And can we do variations of the task? And can we change the environment and still the same program works? Another challenge is, so if the robot knows how to pour popcorn out of a pot, and it sees in a YouTube video another robot pouring water out of a pot or out of another container, can it actually see that video, understand it, and then make very few learning examples in order to basically get that additional skill? And I think what is one of the very basic capabilities that such robot control programs have to have is that they are cognizant about what they are doing. So by that I mean that if you run your robot control program, at any point in time you have to be able to ask, what are you doing? Why are you doing it? How are you doing it? What do you believe at this moment? What are your expectations about the outcomes of your current action? And only if we can basically do that open question answering about the current activity of the robot, we can expect that the robots are getting really competent and really robust. So so what we are doing is we are trying to develop a cognitive architecture for building robot control programs, and essentially the main workhorses in that architecture are these generalized plans and the way that they are interpreted, and a knowledge system like a theory agent that helps the plan interpreter to interpret the generalized plans. So the plans are typically underdetermined, and what the plan interpreter does, it basically identifies where the current specification is underdetermined. It infers what it needs to know to execute the action and turns that into a question that is passed to the knowledge system. The knowledge system then returns a motion specification, and if the plan execution system executes that motion specification, then the hope is that the manipulation task is solved. And I'm briefly talking about the plan representation part, but I will mainly focus about the knowledge representation and reasoning part. So if you look at the fetch and place tasks, the way we have the fetch and place task coded is that we have a plan which is supposed to fetch and place any object and fetch it and place it at any location. And the plan has a very very simple and a very modular structure. It simply says at a location where the object is, you have to perform the action to fetch that object. And then at the location where the destination is, you have to place the object at the destination. Right? So this is yes, please.
Where would you encode constraints?
Oh, they are coming. So they are implicit. So basically, the big idea is that we allow the programmers to do hand waving and say, somehow you should do that, right? And then the system on the fly is actually filling in the gaps and doing inferring the constraints. And I will talk more about that. Yes. So if we look, so this was the high level and the part of the plan that tries to get the information to execute the action. Then we have the low level. The low level is essentially a motion plan. It's a model of how manipulation actions are structured that comes out of cognitive psychology. And there we basically decompose a manipulation action like fetch and place into a reaching motion, into a lifting phase, into a transporting phase, and a releasing phase. So each of these phases has a motion goal. So for instance, the reaching phase has a goal that my hand has contact to the object. The lifting phase has a goal that it doesn't have contact with the supporting surface anymore. And then, so that's an extension from us. So we have knowledge preconditions. So when we basically start our reaching action, we have to know what the target point is we want to reach. We have to decide on a pre-grasp of and a grasp which contains the grasp type and the placement of the fingers, the force, and so on. So in order to execute these low-level motion plans, we essentially have to satisfy the knowledge preconditions of these motion plans, right?
That's another quick question.
Yes.
Maybe you're going to answer this in a second. So the previous slide is what we call sort of happy path, right? So this is when everything goes right, you go,
yes,
you
yes.
lift, you reach. Are you going to talk about how you handle exceptions?
Not explicitly, but the plans are containing about 90% failure detection, failure analysis, failure recovery, and continuation afterwards, right? So, yes. So
in a different system, or is it part of the vocabulary?
it is part of the system, right? So you, it's always your. I mean, the whole plan language that we are using is a plan language that has success and failure as a primitive component. So every subprogram you would call is returning success or failure and a partial failure description that you can analyze. So it's it has a heavy machinery and also control structures to propagate failures, to handle them and to recover from them.
Or are these typically learned, or do the people design these manually, or where?
So in the beginning, so basically, when you look at the failures, we have a failure taxonomy. So the top level is the action just fails, right? And in this case, you only have a failure recovery, try it again, which is very uninformative, right? If you have a better diagnosis, like you couldn't detect the object properly, then you know that you have to reposition the robot or change the detection algorithm. So you're doing refinement, and the better your refinement is, the more promise have the failure recovery methods to actually solve the problem. Okay, so the typical thing is we are calling these very general plans with an action like fetch a cup and put it onto the kitchen table, and the context would be a task like table setting, right? So then we take that partial description and instantiate the body of the general task by these partial descriptions. And then what the system essentially does, it extends these descriptions by these specifications that the motion plan needs, and then we basically have to infer these pieces of information to execute the task. So, and the most essential mechanism that allows the plan interpreter to do that is to have to pose that body motion query to that knowledge representation and reasoning system. So it queries, how do I have to move my body in order to accomplish that partially specified task successfully, right? And it basically does that by asking these different parameters for the motion, and we want that plan to succeed. So some of the big things is that that this goal is only partially specified, right? So if we are supposed to put a cup on the table during table setting, right? So the place of that cup should be on the right side of the plate and behind the plate. And all these kinds of informations, they have to be inferred, and the place where these kinds of informations are the common sense knowledge that everybody from us has, but that is so difficult to explicitly state in robot control program. So the hypothesis of our work is that for these tasks like fetch and place, cast, pour, and so on, we can have one generalized plans which basically specifies the structure of all these actions. And then we build knowledge bases where we basically have modular and generalized knowledge, like cups used for table setting have to be clean and nobody else wants to use that cup. Sometimes people have preferred cups. Clean cups are in the cupboard. Clean cups are typically empty, so I don't have to look out for spilling. Cups have to be grasped on the outside. And so the power of that is, if we are having these generalized and very modular knowledge pieces, then if we get into tasks that the robot has never seen before, it basically can chain these knowledge pieces and has a good chance of doing tasks successfully it has never seen. So something like that a filled open container has to be held upright applies to any container, right? And to any shape of container, and that gives much more scalability to our system. Okay, so and we are trying to do these programs, and this is how that program works. So what you are seeing here is the robot acting in the real world, doing a simple table setting task. Here is a high-level belief state of the robot. You see here the collision environment where the robot does the task planning. Here are the results of the last object detections. Here is a camera view of the robot control system. You see that the robot is actually getting the objects out of different containers, drawers, different kinds. Also that it positions itself, that it sees the objects well. Here you also see, if you are applying these general methods of where the robot should, for example, stand in order to pick up the object, you always see a distribution of possible places where one particular position is picked out of, and then the manipulation action is tried. And these also give examples of learning how to do these motion parameterizations. Yes?
You have these general notions of empty, clean, and things like that, which make a lot of sense to us, but how do you ground them actually in the perception system so that it can detect whether something is clean or whether there's water in a cup?
So like I think in many cases this is not grounded. So in a way, when you say table setting, so some of the knowledge is coming from putting humans into virtual environments and say, set the table, right? And there you would actually see where they get the cups from and where they place them, right? So I don't think executing these manipulation actions will always be under partial knowledge, right? So if you are taking a cup out of the cupboard, you're assuming that it's clean, but you seldomly check, right? Yeah. So yeah, and you see that all these different poses, which are essentially the pre-pose for manipulation, and then the parameterization of the reaching and grasping are done. Here you see a particular difficult object. Yes, and here you see that the same program also scales not only for setting the table, but also cleaning the table, so putting them back into the wastebasket or in the fridge. Here on the upper right, you see that the same program runs on a completely different robot. Here we have changed the environment, and here we have a variation of fetch and place, where we do assembly, where basically the placements have to be particularly accurate. Okay, so this is the way essentially how we write the programs. So the programs are, of course, much bigger because for one thing, it's all the failure handling they have to do, but also when they get the information that they need in order to refine the action, that can only be done in the course of action. For instance, I can only localize the cup when I have opened the cupboard, and so that scheduling has also to be part of the plan. So these plans are written such that every parameterization decision is explicitly coded as a question to the knowledge representation and reasoning system, and the answer is coming back. So we can also use that infrastructure then for supervised learning. And so we can also show if we are mentally predicting the plans while we are executing. So we are predicting that a certain parameterization will fail actually when we are putting down the object. Then the plans are getting, of course, better, and we can automatically specialize the plans through experience-based learning. And there you have effects like if the robot is, for instance, trying to detect plates in a cupboard, so it doesn't have to apply a very general object detector, but it knows from its experience that plates would be just horizontal lines at a certain position in the cupboard, and that perception method is much simpler, much more efficient, and much more robust than applying a general detector for plates. Okay, so let me now talk a little bit about the knowledge and representations and reasoning system that we are using in order to make that kind of decision making for manipulation. So if you look at knowledge representation and reasoning in artificial intelligence, so what is one of the first things that you are taught in artificial intelligence, that your representation is at a very abstract level. So it's about objects that have identity and that stand for the objects in the real world. And if you are looking at actions, it's even worse, right? So your conceptual model is typically a state transition system with atomic state transitions between the states, and you have a model of the preconditions and the effects, and you're abstracting completely away from how the action is executed. If you think of how we in robotics work on these problems, for us it's the main task, the question, how do we implement the motions that implement this action in order to make the action successfully. So because the AI representations make these abstractions, we lose all the opportunities to actually make these huge impact on performing actions in the right way. So essentially what we need are representations which go down to the motion and to the image level so that they can be properly grounded and that they give us the opportunities to optimize. So our proposal for that is that we are looking at a hybrid knowledge representation system, which is composed of a symbolic knowledge base, which is, as it's typically implemented in AI, and an artificial world, which is essentially a scene graph representation of the world together with rendering and simulation infrastructure. Yes, please.
So I noticed in the relative pose you have X, Y, and O. Are those reals or are those still symbols?
Doesn't matter. So it would be actually so whenever we have say a name here, it's actually the name of the data structure in the artificial world or in the scene graph, right? So so basically we have exactly the same level of detail as the scene graph. Does that make sense? Yes.
I think so. So I guess you're saying that when you talk about symbolic, you can have sort of
yes.
mixed
so the
actual
yeah. So the
set by symbols and reals.
Yeah.
Okay.
So we include basically the reals because what we want is we want to generate the artificial world out of the symbolic knowledge base and go back. So we want to have a one-to-one correspondence and yeah. So and of course the assumption is that we are in a world where we know all the objects and have models of the object. Okay, so then we basically want to take this knowledge representations and we want to take the real world. And we want to get the real world and the artificial world so close to each other that if we are executing our robot control program and we look at the execution traces, we couldn't distinguish whether the program was actually executed in the real world or the artificial world. So that's the idea. If we are getting that, then we can play a very promising game. So we can pretend with our robot control program we are executing our program in the artificial world, but in reality we are executing it in the real world. And the big advantage of doing that is in the artificial world we have much better information. We have access to everything. And of course, those two representations will never be the same. So we have to account for that our robot control programs have to have heavy machinery for event and failure detection and continuation. But our belief is that the information that is contained in these very informative models makes it worse to have all that machinery. So we are always monitoring and look at the differences between the real and the artificial. Okay, so let's see whether we can actually generate representations that are matching our expectations. So that's not possible for environments like kitchens, but if you are looking at more structured environments like retail stores, so that is in the reach of getting that done. So we are installing robots in a supermarket, and we equip the robot with models about the products, also models about the furniture pieces, barcodes and separators, and then we let the robot go in the environment, build a symbolic knowledge base of the supermarket. Pardon?
There was a prologue on that slide.
Oh, there is every prologue everywhere, yeah. So here you see the robot in the environment. And here, this is the belief state of the robot. At that point, the robot has detected the base components of the shelf systems, and now it's looking for the individual shelves, right? And now it has detected the individual shelves. And now it's looking for the separators and the barcodes of the products. And now it's going, taking each barcode and see whether the respective objects or products are in that shelf. So we are basically constructing now our artificial world. And so we are able to build a symbolic knowledge base without human interaction, and we can here use Prolog, of course, to retrieve semantic information from that. So we can ask about particular products and where they are. Or we could ask where are all the empty facings in the shelf system. Or by combining it with background knowledge that we have, for instance, from the World Wide Web or other knowledge sources, we can ask questions like, where are products that are dangerous for kids, but they are in the reach of kids, right? And basically any query that you can semantically formulate with your background knowledge is executable on that model. But we can also take that model and construct the artificial world out of that. So basically game engine environment. And now we can go shopping and basically in the model that is acquired by the robot. And because all of that is a knowledge base, a symbolic knowledge base now, and we basically have the models of cognitive psychology, we can automatically pass the actions in the virtual reality and basically get information that we, for instance, can use for imitation learning. So, of course, for robots, the most important thing is, can we actually use these kinds of models to perform autonomous manipulation actions? So there are only a handful of objects that we can manipulate with our grippers, but with respect to the information content, you can see that we can do these kinds of things. And then the question, can we actually do that in real-world environment? So that's in one of the retail chain stores in Germany, and you see that the robot is building these artificial world models of realistic environments. Okay, so this is one part, right? So the other part is, so that was a static environment and that was the deployment phase. But if we are in the manipulation part in table setting or in other case, the question is, can we actually get models of the current state of the environment, and can we maintain these models while we are executing? So this is very early, and we are just starting to develop that system. But here the idea is that we have the robot in the environment, and like in the retail store, we want to build a model of the kitchen environment that corresponds to the current state. And unlike many others, we basically take here the models of the object themselves and place them. And the hope is, because we can realistically render them and feed them back into the perception system, that the redundancy and the simplification of the perception problem helps for making these tasks much more stable and efficient. So, so we would hope when the robot is actually doing its task in the kitchen, it can maintain a complete belief state about the setup of the environment. Okay, so when we are looking at this digital twin knowledge representation and reasoning framework, so we have seen it consists of the symbolic knowledge base, which are essentially the assertions and the axioms. and the artificial world, which provides an environment model through a scene graph, and basically rendering and simulation structure. And then we have two functions that convert from the knowledge base to the artificial world, and from the artificial world to the knowledge base. And what we want to have is, of course, if we are looking at the symbolic knowledge base, then everything we have in the artificial world is true. And on the other hand, if we convert the knowledge base into the artificial world, there shouldn't be other objects than the ones that are already in the artificial world. So that is a consistency condition between two. And then we have that function that whenever that artificial world is evolving and there are intentional activities going on, like the shopping in the virtual environment, then this should be automatically parsed and interpreted and converted in a knowledge base. Okay, so let's look at that. So from the models from cognitive psychology, we know that for the segmentation of the motion phases, the important criteria are the force dynamic events, the hand having contact with the object, objects being lifted from the supporting surface, and so on. So we have instrumented the simulation engine in order to detect these force dynamic events that we need for action recognition. And so here we basically perform kind of a manipulation action. So you also see that we have the fluent flow detected, the start and the end. And here you see the same structure and now doing the online detection and categorization of these actions, the motion phases, and automatically recording the trajectory data that we need, right? So this.
And then are you, in this case, for example, if there's less milk in the, or more milk in the real milk bottle than the demonstration, how would it handle that?
Well, I mean, I guess it has to do that like we do, right? So it has to basically look when you're filling the glass how the level raises, right? And I think that, so it's always a question of, if we are looking at the states, where do we actually try to measure the state, and at which place? And it's so there are always unknown parameters like the viscosity of the fluid, like the surface friction, and we have to, like humans, actually act right without knowing these parameters.
So that's something that has to go into this, because you don't know whether you should simulate actually the tilting motion or whether you should simulate the milk level, right? Or
no, I think in general. So when we are doing all this simulation-based reasoning, we are not doing the haptic feedback loop. So, and I think in general, you would want to parameterize your actions also often in the effect space, and the mapping from the effect into the controllable parameters should actually be through probabilistic methods, right? And so like, you're pouring pancake mix on the oven, and you would measure how fast the pancake grows, right? And that, if you're doing that, you don't need to know the viscosity and the other surface, because you have something that is correlated with that. And yeah, the question is what kinds of manipulation actions we can do these kinds of things. Yeah, and you basically get everything automatically in our knowledge representation system, and you can access it through Prolog. Yeah. And this is the most recent version. Now you can see that we have a full body motion tracking. It's also with physics-based interaction So you can close the fridge by kicking, and yeah. So we are trying to get these kind of simulations also as realistic as possible. Yeah, and then of course that's not a very faithful representation, but it's starting there, right? So you can do things like that you have to grasp a pot plate with two fingers, so one would not be stable enough, and yeah. Okay, the other thing is the symbolic knowledge base. So if you're looking at the artificial world, right? So the idea is that you could click on every object part, and you have a symbolic knowledge base behind it that defines what these parts and what these objects are in a machine understandable way. So whenever you are actually generating your learning problems or you're doing reasoning, you can do that in a semantic way rather than trying to correlate features. Yeah. I think the most powerful mechanisms that we have in that knowledge representation and reasoning framework are the mechanisms that are based on simulation. And because we basically have our environment, and here we have the simulation, there we have the rendering, and then we can realize cognitive capabilities like mental simulation, mental imagery, imitation learning, and motion replay. So mental simulation, we built gazebo-like simulator, but now on top of Unreal. And we basically run the robot control programs in the very same way we run them in the reality. So it's without changes, just exchanging the low level of the control programs. We run them in both frameworks. We can even run perception in that framework. Mental imagery, so that we can mentally imagine scenes that the robot has experienced and modify them, right? So we take the log data we have from the experience of the robot, but now we can replace kind of the milk with orange juice and create situations that are very representative for the tasks we are looking for, right? And then using the semantic infrastructure, we can do things like show me all the objects above the counter, or all the objects that I can reach with the right arm, and all the objects that are above the plate. And so that essentially means that every question you can ask with a symbolic representation language, you can automatically turn into a learning problem that the respective concept is learned as a perception mechanism. Yes, please.
These notions of liquid, container, and things like that. How did you get those into the knowledge base? Did people program some of these predicates? Or?
Yes, so that would be actually, so we have a big encyclopedic knowledge base, right? And there is the concept of a container and a liquid containing container, and they are all defined in terms of logical assertions, right? And that. Yeah, and yeah. So, and the another way of acquiring knowledge, and this is for manipulation tasks particularly important, is if we let the robots watch YouTube videos. So the idea is you want to take instructions, textual instructions, and you want to take the video, and you want to basically combine them to get semantic representations of the actions you see. So here you see what the system is doing at the semantic level. It's basically taking the frame from textual descriptions, then it's filling it out with the parameters that it's seeing in the image. So it's basically saying that it's a taking action, that it's that's a power small verb grasp, and that it's a mug that is grasped. And so you get essentially the same kinds of representations we are using in our plans. So that is then very compatible. And we need to do that because there are many ways of doing manipulation actions, and most of the methods will not succeed on our robot control system. So we have to look at all possibilities to find one that might work. So that's basic system architecture. So you have here deep network that does the pose estimation, here the detection of the object, the hand pose estimation. Here we have a Markov logic network which takes the textual description and then infers parameter that the system cannot see, and the combination basically gives us better information about these videos. And that's what we are working now on. So we are trying to get these observed activities. We try to match it on the avatars in the artificial worlds, and then getting basically the semantics underlying that, because now we are getting force contact, and that should give for imitation learning much richer representations for using. So that's just something where, if you think about artificial worlds being logical knowledge base, right? The question is, what is it that I can actually represent as a logical knowledge base? So how rich can my knowledge bases are, right? So, and this is just a scenario where we have somebody heating food, and later it's basically a cutting action, serving, and then at the end it's the start of a feeding action, right? But now the big thing is here. Now we have multiple agents in the environment. We have interactions, and again, because we have it that way, we could also train the vision systems with these images and try to give the robots better ways of understanding the activities that are going on in an environment. Okay, so that just so basically the knowledge representation system has that large hybrid infrastructure. Everything is wrapped as a virtual logic knowledge base. We can interface through Prolog, and then we have the applications perception, question answering, learning, and recording of episodic memories. So let me just show you what that actually gives to the system. So if you look at the episodic memory, so this is a video on this side which is completely generated out of the Prolog knowledge base. So it's just render the knowledge content of the, and you see that you have quasi-continuous motions of the robot control system. You see object detection, you see the images, and again, that is information that you can use for reasoning and learning. So the data structure of episodic memories are all the poses of the robots. The images it used for major interpretations, the way the plan got interpreted, and then interesting is where the plan interpretation, so the computational execution of the plan, and the real world interface through these force dynamic events and perception events. And they are essentially represented as logical assertions. So to give you an idea of what that does, so we are running our manipulation episodes. The system is automatically recording episodic memories, which are a logical knowledge base. And now we can take that episodic memory and ask the question, is there an action of the type pickup where the robot tried to pick up a pot that has a weight more than 2 kilograms? And we can ask, when did that action start? And we can ask, what is the pose of the robot at that very moment? We can now take that question and use it for generating learning problems, right? So we are now interested in the set of poses in which the robot picked up a heavy object, but it was successful. And we want to collect the poses for which it was successful in pose. So we get the positive examples of picking up a heavy pot. We can also collect the failures, and now we can basically learn where the robot should stand in order to pick up heavy objects. So we are running many samples in simulation. We are getting the green ones as a successful pickup, the red ones are the failed ones. We are learning the places to pick the object at the respective position. And now at execution time, when we see objects with a certain inaccuracy, we back project the place, and now we get more a distribution-like representation of that place, where basically the higher the distribution is, the higher the probability that it will be successful. So here you see how that representation varies when you change the object, the inaccuracy of the object, and here you see it in practice when the robot is supposed to pick up objects from a table. Okay, so yeah, that was all that I wanted to say. So I tried to convince you that besides deep learning based approaches, designing robot control programs in a more engineering based fashion and combining these well-designed plans with lots of knowledge where we basically get these knowledge pieces from very different sources might be also a way to scale the manipulation capabilities of future robots. Okay, thanks a lot for your attention. Yes, please.
So one challenge it seems is that the more knowledge you put into your knowledge base, the longer inference might take. And when humans are in the loop with the robot, the responsiveness of the system might become a problem. So I wonder, what paths do you see forward to keeping systems like this responsive?
So for us, that is not really a problem. And the reason for that is, so from what we have done so far, you don't have these long chains that basically generate huge search spaces, right? So in most cases, it's actually combining different pieces of information in a data log way. So more like an SQL query would do. And those queries are typically very efficient. So that doesn't seem to be the bottleneck, and that basically there's very little search space reasoning that we are doing at the moment.
And there's one big thing coming up these days when people start doing whatever, also deep learning from simulation is, of course, the gap between sim and real, right? Like, and it seems like you still have to bridge that gap also to always go from your knowledge base to the real world and go so that you learn on the perception side. You still need to learn the controls so that the controls actually work in the real world. Any thoughts on how to do that in general?
I think for us it would be much better behaved because we have these semantic events and the structures, they are well structured problem. Not everything is actually a black box, right? And so we basically know that, I don't know, the pickup was successful or it slipped during pickup, which is much better information and we can be much more easily adapted to the real world than if you're having a black box system, right?
Well, no, yeah, it's not only that, but even if you, let's say, you still need to execute that grasp in the real world, right? And
yes.
It's informed by what your knowledge system came up with. So the question is, you need to still generate these low-level control commands, and you still need to perceive the world
yes,
so that you get your states.
So I hope I have said that we are not basically simulating the haptic feedback loop, right? So I think this haptic feedback loop is really one that has to be tackled with probabilistic method, right? So there it's actually, you are making this more POMDP or, yeah. So
that's still something that has to be done.
yes,
okay.
yes. But it's kind of at the local level where you're bottoming out, right? It's not. So I think you have better chance, and then you have these failure detection and failure recovery methods that try to fix it from the higher level.
All right. Thank you.
Cool. Thanks a lot.